Rocks and fossils. Rocks and minerals. All rocks are solid and hard, but they come in an amazing variety of sizes, shapes, colors, and textures. They are all composed of mixtures of materials usually, but not always, including substances called minerals. Some are made almost entirely of one mineral. Limestone is an example. It is composed mainly of the mineral calcite. Most rocks, however, are mixtures of 2, 3, or more minerals. The word mineral is sometimes used for all sorts of substances. For example, many vitamin pills contain not only vitamins, but also minerals. Workers in the mining industry often use the word mineral for any material taken from the earth. They may call oil, gravel, coal, and copper ore minerals. The term mineral, however, is usually used more narrowly by scientists who study Earth and its rocks. These experts are known as geologists. For geologists, a mineral is a solid substance made of one or more simple chemicals called elements. Each element has its own specific type of atoms. Atoms are particles that constitute the building blocks of matter. In each mineral, atoms are combined in a particular way. They form a rectangular pattern called a crystal. Many geologists insist on one more thing before they call a substance a mineral. They require that it not be formed from living things. Mineral medley. More than 4,000 minerals have been discovered on Earth. Color, hardness, and weight are some of the ways in which they differ. A key reason that minerals differ is that they are made of different elements. That is not the only reason, however. How the element's atoms are arranged in a crystal is also important. Combining the same atoms in different ways will produce different crystals, and the results will be different minerals. For example, atoms of carbon that are joined together in one way make diamond. Putting them together in a different way makes graphite. Graphite is black and quite soft. Diamond is transparent and is the hardest substance found in nature. Both diamond, left, and graphite, right, are made of carbon, but they are very different minerals. Graphite is soft, is black or gray in color, and has a metallic sheen. Diamond, formed under high pressure and temperature, is extremely hard. A few minerals are plentiful in Earth's crust. This rocky top layer, especially the portion under the continents, is the part of the planet we know best. More than 98% of the continental crust is made up of just 8 elements. The most common ones are oxygen and silicon. Minerals containing these two elements are found almost everywhere. One mineral, feldspar, makes up more than half of the continental crust. Feldspar is actually a group of related minerals. All feldspars contains not only oxygen and silicon, but also aluminum plus another element. Quartz is the next most common mineral. It is silicon dioxide. That name means it is made up of 2 atoms of oxygen for every atom of silicon. Prized minerals. Gemstones are minerals that can be cut and polished to have an attractive look. They are durable and highly prized. After they are cut and polished, they are known as gems. Gems tend to be valued highly because they are not only beautiful, but also so hard that they resist being scratched. Diamonds are the hardest of all, and they are especially prized. Beautiful, durable, and rare gemstones, such as emeralds and rubies, are said to be precious. Gemstones that meet only 1 or 2 of these 3 criteria are usually known as semi-precious. Jade and zircon are examples of semi-precious stones. 2 of these 4 gemstones, ruby, upper left, and sapphire, upper right, consist primarily of the hard mineral known as corundum. Ruby's red color comes from the presence of a small amount of chromium. Green emerald, lower left, is made mainly of the mineral beryl. Topaz, lower right, tends to be white or light-colored. Ores make up another group of prized minerals. An ore contains a valuable metal or another substance. For a mineral to be called an ore, it must be present in one place in amounts or deposits large enough to make mining worthwhile. Non-mineral rocks. While most rocks on Earth contain minerals, as defined by geologists, Some do not. Coal is one example. It is a rock that was formed from the remains of dead plants. Two more examples are obsidian and pumice, which come from volcanoes. They are glossy and lack a crystal pattern. Rock types. There are three basic types of rocks: igneous, sedimentary, and metamorphic. Each type is formed in a different way. A rock's makeup reflects the way it was formed. Rocks also carry other clues about their history. These clues may reveal when a rock was formed. They may also give hints as to what conditions were like when the rock was formed. There may even be clues about events that have occurred right up until the present. Clues found in rocks can help scientists learn about the history of Earth. Igneous rocks. Most rocks in Earth's crust are igneous. They began as hot liquid material called magma. Magma usually is found at depths where it is much hotter than on the surface. This heat is how igneous rocks got their name. Igneous comes from a Latin word that means fire. If magma gets cool enough, it turns solid and becomes igneous rock. There are many kinds of igneous rocks. Each type is determined by how it was formed. Another factor is what its original magma was made of. Intrusive igneous rocks. If magma cools slowly, it turns into one type of igneous rock. This can happen when magma moves to a part of the crust with a somewhat lower temperature. For example, magma might be pushed closer to the surface through a crack. The magma intrudes or inserts itself into the crack. The new rock that forms when the magma cools is called intrusive rock. Since the magma cools slowly, there is plenty of time for crystals to grow. As a result, the crystals in intrusive rocks tend to be large. Although formed underground, some intrusive rocks later end up on the surface. If you look at such a rock, you can see it in large bits or particles called grains, which contain one or more crystals. The most common sort of intrusive rock on the surface is granite. It contains feldspar and quartz, along with a little mica and tiny bits of other minerals. It is very hard. Its color tends to be gray or whitish, but some kinds are pinkish or even other colors. The colors depend on the minerals that make up the granite. Another common intrusive rock, gabbro, is darker in color. This towering rock face in Yosemite National Park in California is made of granite. It was formed by intrusion of magma, which solidified and later was left behind when surrounding rock was worn away. Extrusive igneous rocks. If magma cools down fast, it turns into a different type of igneous rock. This happens when magma comes out onto the surface. It may come out through an opening called a vent in a volcano. It may also come through a crack or fissure in the ground. Magma that flows onto the surface is called lava. The temperature on the surface is much lower than in the crust, and the lava cools quickly. Since the magma is pushed out or extruded onto the surface, igneous rocks made in this way are called extrusive. They are also sometimes called volcanic rocks. Extrusive rocks tend to have tiny grains. If they cool very quickly, they may even lack grains. They may look smooth, like glass. The most common extrusive rock is basalt. It is dark colored. Its ingredients are similar to those of the intrusive rock gabbro, but basalt and gabbro look different. It is much easier to see grains or crystals in gabbro. Because basalt comes from fast-cooling lava, its grains are very tiny. Many of the rocks brought back to Earth from the Moon are basalt. They were probably formed in the same way as Earth's basalt rocks. Lava poured out onto the surface from below and cooled. A highway passes by the edge of a rock formation of hardened lava. Another set of extrusive rock is rhyolite. It is light-colored and has the same minerals as the intrusive rock, granite. When certain kinds of lava cool very rapidly, the result is a glassy black or darkish rock called obsidian. Obsidian forms sharp edges when broken. Sometimes lava contains air bubbles. It may seem like foam. If the lava is very thick, like molasses, the bubbles can escape before it hardens into a rock. This rock is called pumice. It is full of sponge-like holes and is lightweight. Some kinds of pumice can even float on water. Air also plays a role in another sort of igneous rock. Some volcanoes throw powdery dust or ash into the air. If the ash piles up, it may turn into a soft rock known as tuff. The so-called Giant's Causeway on the coast of Northern Ireland consists of thousands of columns of basalt that were formed some 60 million years ago when an extrusive lava flow quickly cooled. Putting igneous rocks to work. Since ancient times, people have made buildings and monuments from hard, durable granite. It can be polished, so it is also used as a decorative stone. Granite is often used today to make floor tiles and kitchen countertops. Obsidian is shiny and sharp-edged. For ages it has been used to make jewelry, mirrors, and cutting tools. Even today, doctors use obsidian scalpels because they are so sharp. Lightweight pumice makes a good decorative stone. Ground-up pumice is an ingredient in some types of concrete. Pumice is an abrasive and is good for grinding, cleaning, or polishing surfaces. Pumice is also used to make cosmetics and soaps. Sedimentary rocks. Most of the rocks on Earth's surface are sedimentary rocks. They were formed from sediment or material that settles in an area. It might be sand, mud, dust, little stones, or the remains of dead plants and animals. The material may be deposited by water, wind, or even moving ice, as in a glacier. As more and more of the material piles up, its weight generates enormous pressure at the bottom of the sediment. Here, the sediment material is squeezed tightly together and slowly turns into solid rock, a process that may take thousands or even millions of years. Sediment sometimes settles on the seafloor. Sediment is also deposited on the bottom of other bodies of water, such as lakes and on the floors of swamps. Accumulations of sand in beaches and dunes may eventually be transformed into sedimentary rock if conditions are right. Sedimentary rocks can tell scientists a lot about the past. The rock's makeup carries clues about the conditions that existed when the rocks were created. Sediment tends to be laid down in layers, or strata. This layering helps scientists identify neighboring areas of rock that were formed at the same time. Sedimentary rocks also give clues about life in the distant past. These clues usually involve fossils, which are remains or traces, such as tracks or burrows, of ancient living things. Fossils often form part of the materials found in sedimentary rock. These rock strata in Capitol Reef National Park in Utah were originally formed over millions of years when the area was at the bottom of a sea. Later, uplift of land and erosion resulted in the formations that exist today. Putting sedimentary rocks to work. When trying to list the most useful sedimentary rocks, coal may be the first thing that comes to mind. There are, however, many others. Sedimentary rocks are the source of such fossil fuels as oil and natural gas. Conglomerate and other sedimentary rocks play a major role in the construction industry. Limestone is used to make cement. Shale is also sometimes used to make cement, as well as bricks. Limestone and sandstone are important building stones. There are many examples outside the construction industry as well. Gypsum is used as an ingredient in making various products such as plaster of Paris, pottery, and cake icing. Rocks containing phosphate are used to make fertilizer. Rock salt is a primary source of salt, which is an essential component of our diet and is also used for many purposes. Salt is also produced through the evaporation of seawater. Types of sedimentary rocks. Sedimentary rocks can be divided into three types. They are called clastic, chemical, and organic, or biological. The basic difference between these types is the way they were formed. This results in differences in appearance. Clastic comes from the Greek word klastos, meaning broken. Clastic rocks are made from broken pieces of other rocks. For example, sand grains are tiny bits of rock. If these bits are squeezed together long and hard enough, the result is the clastic stone called sandstone. The bits of material in silt or mud are extremely tiny. If they are pressed tightly enough together to form a rock, the result is shale or mudstone. Shale and mudstone are rather soft and have finer grains than sandstone. Clastic rocks may contain rock pieces that are bigger than sand grains. The pieces may even be as big as boulders. Smaller bits of material help to cement these pieces together. If the pieces have spent a long time in moving water, they will have rounded edges. The same is true of pieces that have been moved and tumbled a lot among other rocks. Sedimentary rocks contain such smooth edged pieces are called conglomerates. If the original rock pieces were simply piled up at the foot of a mountain, however, their edges will be sharp. The sedimentary rock containing them is called breccia. Chemical rocks contain principally material that was carried or dissolved in water. Under certain conditions, this material settles on the bottom of the body of water where it may form solid crystals. Another way dissolved materials may separate or precipitate from water is to be left behind when the water evaporates. Examples of rocks formed by precipitation from water include rock salt, halite, rock gypsum, a few types of limestone, and most of the world's important iron ore deposits. In caves, stalactites and stalagmites are formed from minerals in dripping water. Stalactites look like icicles and extend from the roof of a cave. Stalagmites are deposits that build up from the floor. Sandstone can sometimes take rather impressive shapes and sizes. You can see some of the variety of sedimentary rocks in these examples. Conglomerate, left, is a clastic rock containing rock pieces that tend to be smooth or rounded. The pieces in breccia, center, are a different sort of clastic rock, are sharp-edged. Some limestones, right, contain an abundance of fossils. Organic rocks form mainly from the remains of living things. Among the types of remains that may end up in organic rocks are plants, shells, bones, and the skeletons of tiny living organisms called plankton. Lignite and bituminous coal, for example, develop from ancient plant materials. Limestone comes mainly from the shells of tiny creatures living in reefs or on the sea bottom. Chalk is a soft type of limestone. Metamorphic rocks. The word metamorphism means change of form. Metamorphic rocks are rocks that have changed as a result of being subjected to new conditions. These conditions may involve increased heat, increased pressure, or exposure to fluids containing substances that can help alter the rock's makeup. For example, hot water sometimes carries certain chemicals, such as carbon dioxide, that may dissolve materials in the rock, cause chemical reactions, or promote the formation of crystals. Most often, the new conditions involve heat and/or pressure that bakes the original rock. However, the combined effect must not be so great as to cause the original rock to melt. If the original rock melts, it becomes magma. When it cools, the new rock is considered igneous rather than metamorphic. Metamorphism changes any kind of rock, igneous, sedimentary, or metamorphic, into a new metamorphic rock. Metamorphic rocks have some things in common. They are usually harder than the original rock. Also, they contain crystals. The kind of changes that happen in metamorphism depends on the makeup of the original rock and on the conditions the rock undergoes. Metamorphism may alter the rock's crystal pattern or texture, for example, or it may change the original minerals into different ones. Contact and regional metamorphism. When scientists talk about metamorphism, they commonly have in mind effects caused by heat or pressure. There are two chief ways such metamorphism can take place. One is called contact metamorphism. This can occur when a bit of rock comes into contact with hot flowing magma or lava. The amount of rock affected is small. Contact metamorphism can happen at the surface, since hot lava appears there. Usually, however, the conditions causing it are found somewhere deep underground. Another way rock changes is called regional metamorphism. Large amounts of rock are exposed to high pressure or heat below the surface. This kind of metamorphism can happen, for example, below a mountain range, whose weight subjects the rocks below it to high pressure. High pressure and heat can also occur as a result of major rock movements. The outer layer of Earth is broken up into a number of large slabs called tectonic plates. Some are under continents and some are under oceans. Forces from deep below the plates cause them to move slowly. In some places, plates slip past each other. In some places, they bang into each other. The edge of one plate may be pushed under another, exposing rocks at the edge of the high heat that exists deep below. One way or another, rocks in a large region are exposed to enough heat and pressure to undergo change. Foliation. Because of the pressure they undergo, the crystal grains in regional metamorphic rocks are often arranged in parallel stripes or flat sheets. This is called foliation. In a way, it is like grain patterns in wood. Schist and gneiss are common regional metamorphic rocks that show obvious foliation. They form under high pressure and of high temperatures, and they have coarse grains. Slate forms from the sedimentary rock shale under more moderate conditions. It has fine grains and can easily be split into sheets. Marble usually forms from limestone. It has an even texture and lacks foliation. Foliation ordinarily does not occur in contact metamorphic rocks. The most common contact rock, called hornfels, for example, lacks foliation. Instead, it has grains to form even texture. Some metamorphic rock are foliated. They appear to be made of layers. Some are not foliated. This gneiss of Borucher World National Park in Germany, left, is an example of a foliated rock. The fractured quartz seen in the Negev Desert in Israel, right, is unfoliated. Getting to the surface. Most metamorphic rock are formed deep underground, so it may seem strange that they are often found on the surface. How does this happen? Sometimes forces within Earth lift up sections of buried rock. Metamorphic rocks can also reach the surface as a result of erosion, when rock and soil that cover metamorphic rock are worn away. Thanks to these natural processes, many metamorphic rocks are available for a variety of purposes. Scientists value these rocks because they carry clues about their origins. They reveal what conditions are like deep within Earth's crust. Putting metamorphic rocks to work. Marble has a smooth texture, and the best known type is white. Marble is also easy to carve compared with many other rock materials. Because of features like these, it has been used for centuries to make statues and impressive buildings, such as the Lincoln Memorial in Washington, D.C., with its seated statue right of Abraham Lincoln, the 16th President of the United States. Another well-known marble building is the ornate Taj Mahal in Agra, India. Slate is another important construction rock. It is used as a finishing stone for buildings and as a material for roofing tiles and pool tables. Schist and gneiss are also used on building stones. Anthracite, a hard black coal formed from bituminous soft coal by metamorphic process, is an important fuel. Rock changes. Constant activity. With rocks, change is always going on. New rocks are constantly being created on Earth. Right now, metamorphism is occurring all over the world. Hot lava is cooling into new igneous rock. Sediments are hardening into new sedimentary rock. Meanwhile, many old rocks are undergoing various kinds of changes. Some may gradually wear away or erode. Others may be broken up by the growth of tree roots. Some may slowly break up as a result of weathering. Weathering includes various processes. Rocks may be eaten away by chemicals such as acid in rainwater or in substances from living creatures. Rocks may also be slowly broken down by changes in temperature, by freezes and thaws. Horseshoe Bend in Arizona vividly shows the power of erosion. The Colorado River has carved a spectacularly curvy path through the rock. Movement on Earth's surface is another major cause of change in rocks. Glaciers, rivers, and landslides move rocks from one place to another. In the process, the rocks are knocked around and break up. Alternatively, they may end up in a place where conditions, such as temperature and pressure, are quite different. Movements below the surface of Earth also cause change. Rocks may be affected by the flow of magma from one place to another. The movements of the tectonic plates lift up land in some places, creating mountains, and cause land to sink in other areas. Earthquakes involve sudden movements of huge masses of rock. Some rocks may be altered by the new conditions they end up in. Some may be destroyed by the shock of the quake. Mount Belukha, located near Russia's border with Kazakhstan, is the highest peak of the Altai Mountains. The movement of mountains' glaciers can drag rocks from one place to another. The rock cycle. Earth is more than 4 billion years old. For virtually this entire time, it has consisted of more or less the same amount of matter. Meteorites and other objects coming from space have added some, but the amount is small. As we have seen, rocks are constantly undergoing change. At the same time that old rock is being destroyed, new rock is being created. The old rock is recycled to make new rock. Scientists call this process the rock cycle. To see how the process works, start at any point of the cycle and follow it step by step. Let's begin with hot magma. Suppose the magma moves into a cooler underground region or erupts into the surface. It then cools off and forms igneous rock. Underground igneous rock may be brought to the surface. It may be carried there by movements in Earth's crust. It might end up there because the rock and soil above it were worn away. Igneous rock can even form on the surface when lava cools. No matter how it gets there, igneous rock on the surface undergoes erosion and weathering. These processes slowly break it down into tiny pieces. The pieces may be carried away, perhaps to the sea. When a lot of this material collects as sediment in one place, the pressure on the lower part of the sediment may be great enough to turn it into sedimentary rock. If the sedimentary rock happens to undergo high heat and pressure underground, it turns into metamorphic rock. The metamorphic rock may come into contact with very hot magma. It may be crushed between tectonic plates. It might be pushed deep into Earth where it is extremely hot. Any of these events could make the metamorphic rock melt and become magma. Then the cycle can begin again. The three basic types of rock, igneous, sedimentary, and metamorphic, are interrelated. Rock of each type can be turned into one of the other types. Scientists call this interrelationship the rock cycle. Actually, there is more to the cycle. Rock of each type can be turned into one of the other types. Rock of each type can also be turned into new rock of the same type. Any rock exposed to sufficient heat and pressure can melt. This means that, under the right conditions, igneous and sedimentary rock can be turned directly into magma. When the magma cools, new igneous rock results. Also, erosion and weathering can affect any type of rock, not just igneous. Thus, under the right conditions, metamorphic and sedimentary rock may be broken down to form sediment. This sediment may accumulate and may eventually form new sedimentary rock. In addition, sedimentary rock is not the only type that can undergo metamorphism. Under the right conditions, igneous and metamorphic rock can also be changed into new metamorphic rock. Layers upon layers. Sediment usually accumulates on a flat surface. As conditions change over time, the sediment may change in content or in the rate at which it is deposited. When sedimentary rock eventually forms, these differences in sediment give the rock a layered look. The layers, or strata, can be easily seen when something exposes them to view. For example, erosion by a river may create a canyon in whose wall sedimentary layers are visible. Road builders cutting through rock also may expose sedimentary strata. The thickness and makeup of the strata in a particular area can tell geologists much about what happened there in the past. The strata's makeup may include not only minerals, but also fossils of ancient living creatures. Scientists often find similarities between certain strata in different parts of the world. This may mean the strata were formed at the same time. By studying each strata and fossils found in them, geologists sometimes can discover what conditions were like over a wide area of the world at that time. These rock strata have been shaped into a vertical position by forces within the Earth. Two basic principles. A couple of basic principles guide geologists in their work. One is called superposition. This is the idea that in a stack of rock layers, the higher strata tend to be younger than the lower ones. So as you go lower, you go farther back in time. Another basic principle is called original horizontality. This means that when sediments were originally laid down, they formed flat layers approximately parallel to the surface of Earth. Although these two principles are helpful, geologists usually need more information to understand a series of layers. Over millions of years, many events might interfere with sedimentary strata. For example, a flow of magma might make its way into the layers. Another possible event is an earthquake, which might cause a break in the strata, shifting one section in one direction and a neighboring section in the opposite direction. Such a break or fracture is known as a fault. Forces in the Earth's crust can cause movement of rock along a fault, which is commonly at an incline. Faults are classified by the direction of this movement. In a normal fault, the blocks of rock on each side of the break are pulled apart by tension forces, and the block overlaying the brick, called the hanging wall, moves downward relative to the other block, the footwall. If compressive forces are involved, however, the blocks are pushed together and the hanging wall moves upward relative to the footwall. In this case, the fault is called a reverse fault. If the inclination or dip is greater than 45 degrees, it is a thrust fault. If the dip is 45 degrees or less, in a strike-slip fault, the movement is horizontal. Also, pressure within Earth might cause the layers to tilt or even bend into a fold. The layers are no longer horizontal, a telltale sign of movement according to the principle of horizontal originality. Need for caution. Geologists need to be cautious when they draw conclusions. It is possible for powerful forces within Earth to shift older strata on top of younger strata. In that case, the principle of superposition does not apply. An unconformity is another factor that can complicate the job of reading history from a series of layers. An unconformity is a gap in the series where some layers seem to be missing. The layers above the unconformity is much younger than the layers below it. There are various possible reasons for such a gap. One is that the missing layers were eroded away before new strata were laid down. Another possibility is that environmental conditions changed and for a certain period, no sediment was deposited. If you enjoyed this story and would like to learn more about rocks and fossils, please check the links in the description box below. Make sure to check out my merch shop too. Thank you for watching, and make sure you like, share, and subscribe.